on anything? Anybody? Questions related to any of the homework or anything up to this point? I feel we should do one of them at least, but.
I used to have.
Yes, sir. Yes. 49, okay. All right, I prefer problems that actually have drawings. This is a word problem. Now you have to make sure you understand what the words mean. And on the quiz and exam, usually, with very few exceptions, I'll provide a circuit. That way it makes it crystal clear. You don't have to wonder. But nevertheless, you should know how to do this. So this one says an industrial power plant operates under the following conditions. And so anytime they talk about, and this is, by the way, single phase, the load is 40 kW, so here's the load, and it has 40 kW of real power. It's dissipated. The line voltage is 220, so here they're saying it's plus to minus 220 volts RMS. That's not peak, it's RMS here. Oh, okay. This is something where you have to calculate the capacitance to put in parallel with this to change the power factor. I did not cover this, but it's in the reading. How many read that section? Okay, I'm glad you did, because this is not, it's not going to be hard, but you're going to have to understand why you're doing what you're doing. But first, let me get to this thing. So it says, and you'll need this, the frequency is 60 hertz. Now you're going to need the frequency. And the power factor is 0.8 lagging. So this one has a power factor of 0.8 and it's lagging, which is normal. Determine the value of a capacitance which, when placed in parallel with the load, will raise the power factor to 0.9. Okay, so let me go through this first of all and show you in the book, just so I can give you a reference point if you want to read more about this. This is in complex power. It's on page 218 if you can write it down. Complex power. Let me take a moment before I do that problem and talk about complex power. Now please be attentive here. This will be on the exam and it can be confusing. It's more threatening than confusing. Once you see it, it's like no big deal. But until you do, you'll have problems. Are you ready? So what is complex power? Well, the symbol for it is S. It's just complex power. And the formal definition for any component, and it really doesn't matter, if you have a voltage V across here, I'll just call it VRMS. Remember, it has an angle as well. So it's going to have an angle, theta. And I'll just call it theta V. And there's a current flowing into the positive terminal, IRMS. And it has an angle, theta I. Now I'm trying to show you this in polar form. There's a voltage, some magnitude and angle, and there's a current, magnitude and angle. Now, if it is a pure resistive load, if this is just a resistor here, then the voltage and current are what's called in phase. The angular difference will be 0. Y'all follow me? If one was at 45 degrees, the other will be at 45 degrees. If one was at 0 degrees, the other will be 0 degrees. If this was a capacitor, if the voltage is at 0 degrees, the capacitor's current would be at plus 90 degrees. Do you all follow me on this? I'm just making a point. There'd be a 90-degree difference in current and voltage for a capacitor. If this was an inductor, and we had J omega L as the actual impedance, then the voltage, if it was VRMS at 0 degrees, the current would be IRMS, but it would be at minus 90 degrees. Do y'all follow me? That's that Eli the Iceman thing. Everybody with me? How many understand that, at least in concept? All right, now, the complex power is really, for any element at all, it's VRMS, and that's assuming that inside here there's both magnitude and angle times IRMS conjugated. Assume for conjugation is an asterisk. How many have heard of conjugation before? Everybody in here technically should have been exposed to it in your math courses and your engineering courses, but I want to just mention it again. If you have the number A, and I'm just going to make up something, say 10 at an angle of 30 degrees. A conjugate is nothing more than 10, same magnitude and angle of minus 30 degrees. The sign on the angle changes. Do y'all follow me if it's in polar form? How many understand that? Just to be clear about this, do y'all understand this right here? Now, if you have something where you have, say, B is 10 plus J10, then B conjugate is nothing more than 10 minus J10. It means the sign on the J would change. Everybody follow me on this. That's all the conjugation means. It appears a lot of times when you're doing any kind of complex variable analysis, and it's something you have to be somewhat familiar with in engineering. So over here, if we look at this, what I've shown you here, and this is a bit, I know there it implies that the angle is inside, that VRMS has an angle at the IRMS. If I would take this example, and let me just make it clear with numbers, so that way you'll see it a little easier. I'm going to make this current 10 amps at 45 degrees amps. That's going to be the current going in here. Can anybody follow me? Now I'm going to say this VRMS is just 220 at 0 degrees. Matter of fact, make this minus 45 degrees. I want to do this to make it a little more pertinent to what we're talking about. Y'all follow me on this, class? The complex power associated with this element, and I've eliminated everything but the circuit element I care about. The complex power would be VRMS, which is just 220. And it's at an angle of 0 degrees, so you don't even need to worry about the angle if it's 0 degrees. Times IRMS times 10, but it's conjugated, which means the sign on that angle changes. So it'd be at an angle of plus 45 degrees. Everybody follow me on that? I'm just giving you a concrete example so you understand conjugation, what we're doing. Now if you plotted that, and that's what they're after, if you plot this, what's called a complex plane, this is S, and it's the complex power. If you look at this, and this would be the real axis, by the way. I'm trying to be absolutely consistent with the book, and this is the imaginary axis, or the J-axis. When I look at this, it would have a magnitude of 2,200. Can everybody see that? 10 times 20. So it's got a magnitude of 2,200 or 2,200. That's at 45 degrees. So what you would draw is a line out here. Here, this would have a magnitude of 22,000, and the angle here would be 45 degrees. This is the complex power. Do y'all follow me? Now, the real power that you're used to is on this axis. So if you take the projection of this vector here, this would be the average power, and it's nothing more than 220, or 2,200 times the cosine of 45 degrees. That's called the actual, that is the real power, that is the power dissipated. But there's something that's termed the reactive power. and it's this guy right here. So on this axis over here, we're gonna have a value of J 2200 times, and it would be the sine of 45 degrees. 45 degrees, sine and cosine are the same. You all follow me? The symbol for this, by the way, consistent with the book, is called Q. This is actually JQ. Now Q is just a symbol for reactive power. You all with me? It's just a symbol. Doesn't mean much other than that. So when you talk about complex power in general, I'm going to put it up here. In general, S complex, the complex power is going to be V, whatever the voltage is, but it's magnitude and angle, times whatever the current is through that element conjugated. And that will have, and the real part is the average power that you've learned about, and the imaginary part is JQ, and that is the reactive power. Get the idea? Now, the reactive power is something you would like to get rid of. It does no good for anybody. It's just extra energy that has to be provided per cycle to the circuit. You would like to get rid of it, and the way you can is by adding a component, typically a capacitor, to any kind of circuit that's dominated by an inductive reactance, which this one is because the angle here is actually behind it by 45 degrees. Can you all follow me, at least in the ideas? I'm trying to make sure you understand the concept. I'm going to keep going with this example. So I'm going to come back to this, but before I do, I want to keep going with this one and try to make the point with the example I've started. So far, do you understand what I'm doing over here? Everybody? All right. I'm trying to show you what complex power is with a real numbered example. Now we're going to talk about how to get rid of that imaginary part by adding an element. I'm going to do it right here. This is where my lecture was going. It's going in a different direction than I wanted to. We're going to assume the frequency is 60 hertz for this problem too. So let me add a little more to this problem. This is the current. I got 10 at 45 degrees. So I'm going to say that is the current here. I is 10 at an angle of minus 45 degrees amps RMS. That is the voltage. This is the voltage, the line voltage there. Now what I'm going to do is say, it really doesn't matter what else is over here. I'm going to add an element to this thing, a capacitor, and I'm going to change that power factor. And here's something I have to tell you. Whenever you talk about powers, and here, everybody sees these two loads, this load and this capacitor are in parallel. You all follow me on this one, class? So the total complex power associated with the load and the capacitor in parallel with it is just the complex power at that load plus the complex power here. Everybody with me on this? Now here's the kicker. The complex power associated with this capacitor, unlike this one that has a positive JQ, will have a negative JQ. So when you add them together, you reduce the amount of complex power. That's the goal. Follow me? We can get rid of it entirely, and I'll show you how. Now make sure you be attentive here. So I have this drawing that I've shown you. And now I'm going to talk specifically about a capacitor that would eliminate the reactive component. Right? And what would the power factor be if all of a sudden all the power was real? Class? It's 1, isn't it? The cosine of 0, it would be 0 degrees is 1. How many understand that? Please make sure you keep up with this, or when I start discussing this, you're going to be left wondering what I'm talking about. You have to stay current on this stuff or you can get terribly confused. Okay? I mean this, because I've taught this course a bunch of times years ago, and I've realized there's certain points in it can be very confusing, and this is one of them, right here. So back to this example. Got 220 volts. I've assumed that this is the voltage and that is the current. I didn't show you the inductive reactance of the resistor causing it, I just said that is the power. You all with me, class? I mean, that's the current voltage, and this is the complex power right here, S, associated with that. So, now we take a look at a capacitor and what the complex power would be of the capacitor. I want you to be very attentive here. So if you have a capacitor, and it has a voltage, and I'll just use VRMS. So if I have plus or minus VRMS across that capacitor, there's going to be a current that flows in that capacitor, right? There's going to be some I here, and I'll call it I capacitor here. And the capacitor has a value of C. It has a reactance of what? 1 over J omega C would be the impedance of the capacitor. How many of you know that? All right? With me on this one, class? All right, so now, and I can do it this way too. I can say, well, I know that I through a capacitor, or really, I through a capacitor is equal to C dV dt in the time domain, or I in the phasor domain through a capacitor. Well, anytime you have a time derivative where the voltage is assumed cosinusoidal or sinusoidal, you just bring out a J omega. So this would be J omega C times the voltage on that capacitor. Can everybody follow me on this? How many understand that right there? You could just take voltage, divide by 1 over J omega C. Do you all follow me? Voltage divided by impedance, you would get the current as well. How many understand it? I mean, just take a look at this. The voltage is VRMS. If I divide it by 1 over J omega C, it just means J omega C comes to the top. It's J omega C times IRMS would be the current. Everybody follow me? Can you see? So with that in mind, this capacitor right here has a complex power, and this is only for the capacitor, of VRMS, we'll just assume it's VRMS at 0 degrees, at 0 degrees times IRMS conjugate, right? You all see how that would be the current through the capacitor. Can you see it in the far back, by the way? Back there, guys? So conjugation does what to this? Class? What happens to the J? Minus J. You all with me? So this becomes minus J omega C times VRMS, or simply put, a capacitor has a complex power that is equal to minus J omega C times the voltage across that capacitor squared. And this is the thing you get. Everybody got that? Just write this down. I'm giving you things that you underscore and you have to know. Not may know, I mean, not kind of know, you gotta know it. All right. Now, coming back to this problem. The voltage is 220. What I want to do, I'm not doing the problem he gave us, I'm doing this my problem, the problem that actually in industry you would want to do. I want to get rid of this plus J 220 times sine of 45 degrees. I want to add something to it that would negate it. You all with me? So you'll notice this is a plus J. You all see that? You'll notice this is a minus J. Follow me? So if I take the magnitudes of this one and set it equal to the magnitude of this and solve for the value of the capacitor, then I will get a power factor of 1. How many understand that? All right, who doesn't understand? You guys, I'm trying to be clear. And I'm not sure a better way to do this. Everybody see, if this has a positive J 220 times the sine of 45 degrees. Do you agree with that? To be real clear about it, this would be what? J, and this would be 220, or I'm sorry, 2200 divided by square root of 2. That would be the actual value. Do you agree with that? Sine and cosine of 45, or 1 over square root of 2. Now, I'm going to set that. I mean, I could just add this term plus that and set it equal to 0, But what you actually see happening is that the omega C VRMS squared is going to be equal to 2200. This is 2200 degrees, 2200 divided by square root of 2. And if you don't mind, I'm going to do it right here. Or maybe I'll do it right here. So I'll take 2200 over the square root of 2. That's the magnitude of the positive J term. And I set it equal, because I want a power factor of 0. A power factor of 1, which means an angle there. There's no reactive power, no plus or minus JQ at all at the end of the day. And then I take that, omega C times VRMS squared. Well, the voltage is 220 RMS. You all see what I'm doing here? How many do? All right, now, question to people. What is omega there? We're solving for the capacitor, but what is omega? Anyone? Speak up, what?
377.
Okay, what he's saying is 2 pi times the frequency. Y'all follow me? Make sure if you don't know that, you'll know it after today. So the frequency is 60 hertz. Omega by definition is 2 pi times f, or it would be 120 pi, and that would be radians per second if you wanted the units. Y'all follow me? Not degrees per second, radians per second. Okay? So with that in mind, now I'm going to calculate C. Everybody understand where the equation came from, right? Somebody's going to have to help me on this. So I can see that C itself right here will be equal to 2200 over the square root of 2. And then I have to divide that by 220 squared, and then by omega, or 120 pi, to get a value of C. Would somebody be able to tell me what that is? Just take 2200 over the square root of 2 over 220 squared over 120 pi. I'm just curious myself. I have no idea. Oh, I guess I could get an idea, but I don't feel it.
Be 85 microfarad.
85 what?
0.3 microfarad.
Anybody confirm that? Microfarads? Micro? Or mil? Microfarads? Okay. Anybody else? That's reasonable. Let me just say one thing about this. And some of you may be working in industry, you're going to have to make some kind of decisions on it. The value of the capacitor is one thing. That's a very easily to achieve value. But the thing you want to do in industry is you want to make sure your capacitor has a voltage that'll be rated for a breakdown strength where they can't exceed a certain voltage. Make sure your capacitor has at least double the voltage on the line, the RMS voltage. There it's 220. You would want something that could withstand 440 volts at least. If you ever work in industry, this class is an application-oriented class. It's not just abstract theory. And the reason I'm saying this is when you get lightning events like that, transients on the line, you're going to get huge voltage spikes. And what happens is if that voltage spike is sustained for any length of time, the capacitor's dielectric will break down, it'll rupture, it'll tear through just like lightning tears through the atmosphere, and it'll destroy it. So this is a practical thing if you ever work out there. Some of you in industry, when you're dealing with things with energy scavenging technologies, now MEs are probably the people I'm speaking to, you're going to be dealing with a whole lot of that in the future. And if you're going to be in any kind of cutting edge car development, stuff like that, the brakes, everything are energy scavenging. Make sure you don't forget to design things if it says it can stand 220 volts and your idea of what you estimate the worst possible case is 200 volts, so oh, it's okay. No, it's not okay. At least double it, preferably go up by an order of magnitude if cost isn't too bad, because you have no idea the kind of crazy transients that happen on these things. From everything from lightning to when you break a wire and it's got a lot of current, what happens is wherever that wire is connected, it will get an immense voltage to try to sustain that current. I'm not gonna get into this too much, but just watch out for things like that. I've had my fair share of disasters because I didn't overestimate what could happen, or correctly estimate just how bad the transits could be. Anyway, you follow me on that, guys? Now we're gonna do the problem he asked, but now with this in mind, we're gonna do it, all right? And this is 49. It's a, just to show of hands, how many tried that problem? So you had to do some background reading if you even took a shot at it, which I appreciate. But this is a really good problem because here he doesn't want to get rid of it. What he wants to do is improve the actual power factor, which I don't like. I like to just get rid of it, but I understand the reasoning for this. In the real world, a lot of times in industry, you don't want things to work perfectly. You just want a power factor you don't get fined for. So they'll put things together that will prevent them from getting fined, even though it's not the best scenario for power delivery. Okay. Back to that problem. What they had was, they had a load, you tell me if I'm wrong about this, but they had the actual average power here be equal to 40 kW, is that right? And then they set a power factor of what? I know it's lagging.
0.8.
Of 0.8, it's lagging. And then they had a voltage here across that of plus to minus 220 volts, right? That's RMS. Always put this at 0 degrees unless they say it's not. Always assume it's 0 degrees. Y'all with me, class? Don't ever make the problem more complicated than it needs to be. Now, that's the power factor. Let me sketch out what it's called the power triangle, what the complex power would look like for this. You with me? All right. So, I know it's lagging, so, and I got 220 volts, and the average power is 40 kW. So when I take a look at the angle associated with that power factor, and I've made this angle 0 on purpose, I know the cosine of theta v, which is 0, I'll put theta v minus theta I here, is going to be 0.8. So that means theta v minus theta I would be the inverse cosine of that, right? And is that 36.87 degrees, or is my memory failing?
Yes.
Is that right? We did this last time, I think. Correct, class? All right, now I made the actual value of theta v is 0 degrees, but remember this is plus or minus, isn't it? We know that's what we ended up with. I made theta v be equal to 0, correct? The angle associated with the voltage. Can everybody see this and understand what I'm saying? So that means theta I, or the angle associated with the current, is 36, plus or minus 36 degrees, 0.87 degrees, right? How do we get the sign of that? How do you know the sign? Anyway. Or it is negative, right? The angle is behind the voltage angle, the current. How many understand that? Make sure you do. Far back, guys. I don't know if there's a game on right now or not, but whenever I see laptops popped up and people smiling and looking, you gotta see it during basketball season from my perspective. They all have these games on. I can pretty much tell how Auburn's doing just by the faces. Anyway, this is going to be negative. All right? So that means this current, whatever it is negative, correct? Now here's what it also means. Now we'll look at the complex power. I know it's VRMS times IRMS conjugated, right? The voltage is at 0 degrees. The current here conjugated, if the current as an angle that's negative. When it's conjugated, it would be positive. How many see that? So now, take a moment and convince yourself. I'm going to draw what's called a power triangle. Or really, it's the complex power plot, but they call it the power triangle. So over here, this is the real axis. And that means this is the average power. This is the imaginary axis, or the j-axis, and this is jq. So without anything, I know the angle is 36.87 degrees. When I conjugate, it becomes positive. It means this, when I look here, I have an average power, PF here, of 40 kW. So that's out to here. Now I know that this is the complex power S. I'm trying to show you the diagram with a triangle, right? I know the angle here is 36.87 degrees. First, convince yourself. How many understand that? All right, with me? Far back, guys? Guys, over here? All right. Now, what I wanted to take, this is 36.87 degrees. I need to find this value. You can get it a couple different ways. How would you get that value? Whenever I see a right triangle and I got one side, I'm either thinking cosines or sines or tangents. In this case, how about we use tangent, right? If you look at this, this is what I want, the JQ, right? I've got this at 40 kW. Do you agree with this? So if I take a look at this, I have Q, or the opposite over the adjacent, or 40K, would be equal to the tangent of 36.87 degrees. And that means Q, or the imaginary component there, is going to be equal to 40,000, or 40 times 10 to the third, times the tangent of 36 point, I'll get out of the way in a second, 87 degrees. First, do you agree with that, everybody? It's not hard to see, but you have to make sure you see this. The only thing I'm trying to do is figure out how much JQ is there based on that triangle. And it's just a right triangle, it's a straightforward thing. Can you give me this value, by the way? J what? Say it again.
30.
33 or
30.
30. So it's 30K. Now, I want to tell you something else about the units that's going to bother some of you. The units of power, because the real power that's dissipated, are in watts. This is reactive power. And in the book, I'm going to try to give you a drawing. That's something called, it's reactive power, or VAR, volt amp reactive. And he shows us on page 219, he says the average power is in watts. The complex, or the, call it the, it should be in VAR. Q, yeah, there it is in volt amperes reactive VAR. The units on this one technically are VAR. I'm not going to sting you on this one. Technically, they all have to be the same unit. You know how a Napier, basically, I'm trying to think of something that uses, think of a lot of things with electrical. There are certain things where they have to have the same units, like Napiers in degrees, believe it or not, have the same, quote, units. They're different. The reason they use Napiers for an attenuation in degrees has to do with an angular measurement. It's really radians, not degrees. But what I'm trying to say is they technically have the same units, volt amps, but when they use watts, that's power that is dissipated. When they use VAR or kVAR, volt amp reactive, this power is never dissipated. And then they just say S is volt amps. Now, I'm not in any way, shape, or form gonna sting you on that at all with units. It's confusing enough without that. When I ask for that, if you would put, if you put something with KW here and accidentally put KW here, you're not gonna get stung for it. You all with me on this? I'm just trying to be fair about this, because some of this stuff gets a little irritating. After your math courses, and they teach you that units have to be the same, and then all of a sudden they're different, and then they explain to you they're not really different, just a different word to mean a different thing. It gets a little confusing. Okay, now, y'all see what they want there? We've got it, right? But what do they want? They want a power factor of 0.9, right? So that means what they want to do is reduce this angle or reduce the amount of reactive power. Can everybody follow the thoughts here? With me? Right here. I'm going to redraw that over there. Please be attentive here. This is the stuff that stings people. So, what I've got over here that's the old power triangle. And what I would do on your papers and stuff, this is the first thing you draw related to the actual load you're given. And by the way, they could give you S, they could give you the average power here, or the reactive power in the angle, but they have to give you enough information so you can create that power triangle. You all with me on this, class? And I would write old, where that's where you started from, and here's where you want to go. Then write new. So we want this. Here's the actual real power. Here's the imaginary power, or J. Now, the average power cannot change. You had a capacitor, it can't change the average power dissipated. The real power is the same. Out to here is 40 kW, and that's actually PAV here. That stays the same, but something does change. The power factor was 0.8, or the cosine of this angle was 0.8, right? Now the cosine of the new power factor, when you add this capacitor, that I'm about to show you here, when I add this capacitor, now the power factor becomes 0.9. That's stated explicitly in the problem. Y'all follow me? So now we're going to draw that new triangle. So first, we know the cosine of the angular difference between voltage and current, but because the voltage is at 0 degrees, it's really the angular difference of the current angle is going to be 0.9. Does everybody understand where that came from, class? So what's that angle, somebody? 25 degrees, something like that? Inverse cosine of 0.9, anyone? 25.8 degrees. Confirm that, anyone? Okay. Now, what I do is, and you'll see it's lagging, so it's still, this is called the first quadrant here. The complex power is still here. You all with me? So now, I come over here, I'm trying to draw this. This angle is 25 degrees, 25.8 degrees. And now I need this value. Now how do you get that value JQ? The tangent function would be good, probably. You agree with me? Sure. So to get this JQ, I can take Q over opposite over adjacent, or 40K, and that's the tangent of 25.8 degrees. So that means Q is equal to 40,000 times the tangent of 25.8 degrees. And what is Q then, someone?
19.37.
Say it again, 19.37.
19.37.
times 10 to the third. All right, 19.37 kVAR. Pardon me? Is that right? How many got that? Just help me out here. Okay. So I know this value, right? I'll go ahead and put down J 19.37. I'll just put times 10 to the third, so you don't get a mistake. I hope you can all read that. Now, where did that come from is the next obvious question. Well, I started with this, J30K, right? When I added the capacitor, it went down to this value, right? So what's the value of the capacitor, or the reactive component of the capacitor? Well, it's going to have a negative sign, we know that, right? It's going to be minus J, but the magnitude would be what? Joe, mind if I erase this right here so I can write? Okay. I mean, I hope you got a copy. Give me 1 second. You're right. Bless you. So here, I'm going to say this, for lack of a better term, the delta Q, the change in the reactive power, is going to be, it goes from 30 times 10 to the third minus 19.37 times 10 to the third, just about 10, or what is that?
7.627.
Times 10 to the third, right? You'll notice that's the magnitude. I know it's going to be something that's going to reduce it. You all with me, class? And I know for that capacitor, the complex power associated with capacitor, I'm just going to put it here. This has a complex power equal to minus J omega C times the voltage squared. Y'all with me? I'm just putting it down there so it rings bells and you keep it. I know that added to a positive J would reduce it. So what I can do here is this. I know that's the total change, and I know the capacitor is going to cause it. Do y'all follow me, class? So what I'm going to do is just set that equal to, I'll put omega C times the voltage squared is equal to 10.627 times 10 to the third, and then I'll solve for C. This is at 60 hertz, am I correct? Is it say 60? Okay. So it's equal to 10.627 times 10 to the third. Then it's divided by 120 pi. The 120 pi is omega, or 2 pi times 60. That's all that is. You with me? Then I have to divide by V squared. Now the voltage is 220, and I have to square it. And then I'm going to erase this too. So what is the value of that capacitor? And that only brings it down to a power factor of 0.9. The reason that problem is probably created by Dr. Irwin is because a lot of times those industries don't want it. I mean, the industries that used to be here, the mills, they don't want to buy enough capacitance or do enough things to bring it down to a power factor of 1. They just don't want to pay the fine. Yes.
Why do you set it equal to Q or change it?
What did I do? What?
Why do you set like omega C V squared equal to Q?
Well, I know that this is the difference. JQ was 30 here, right? I added something to it that reduced it. Over here, I got it down to 19.37K, right? The thing I added was the capacitor. The capacitor would have, it would be adding a minus J something to that positive J something, and it would bring it down, reduce the total magnitude. So when I got the total difference of that from the start, the old to the new, I simply knew that had to be equal to the actual effect of the capacitor added, and that would be, or the complex power associated with the capacitor, omega CV squared. That's right. Any other, thank you, Sydney, but that's probably somebody else had questions about that. it's very important that you see the reason why I'm doing this. Now, one of the problems with this is, first, I used to assume everybody sees omega every day of their life. They don't. Omega is an important frequency. It's not F, it's 2 pi times F. Just remember that. I used to think everybody used this all the time, but I've learned since then it's not quite true. The second thing is this voltage and the current, not quite yet, are all RMS values. They're not peaks. It's very important to keep that in mind. Now, I'm not going to try to trick you. If they're power-related problems, they will be RMS values. You're with me on this, class? There's no tricks here, but you have to understand. One last thing, all right? I got a question about the quiz on Friday. I'm going to let you decide this because I'm going to be as fair as I can with this. So this is my opinion, the quiz averages has been going up, just leveling from what I see. I don't track it exact, but I can see the trend and the averages. How many want a quiz Friday? We're going to have a test the following Wednesday. How many want one? All right, how many do not want one? Can you turn around and look and verify what I'm about to say? How many do not want one? I think it's a majority. Do we agree with that? All right, I won't give you one on Friday if you don't want one. More quizzes the better, and I won't give you one on Monday, but here's what I'm gonna do. On Friday, I'm gonna cover this stuff, and we'll probably do, we're gonna go into, make sure I don't say something else. This book's it's set up a little differently. What I want to do on Monday, if you want me to just be straight with you, I want to do part of that session at least on a review. That's what I'm looking forward to. But hold on for 1 second. All right. We'll start in the following chapter, but I'm going to be very clear what you're expected to know up to the exam. It's comprehensive. I'll tell you right now, if I was sitting where you were, if you did not understand transients, you didn't understand RLRC, go do it. Get out of the way whatever you don't understand, now's the time to understand it or ask me questions about it. Understand Thevenin, understand nodal, understand mesh. Please make sure you do that. Try to, in the time before the exam, earliest time, work on the stuff you have problems with, you don't get problems on. That's my opinion, yeah.
Do you have a question as of right now?
What? Oh, he's asking how many problems. Usually 4 specific problem statements, like the quizzes, right? 2 or 3 questions related to that topic, all right? So it's a total of 4 different topical areas. And then, but they're multi-part questions, just like the quizzes. If you look at the quizzes, that's like problems on the test. The biggest problem with those things, in my opinion, is knowing how to use your calculus, because people foul these things up all the time on their calculus. And I think you guys come to terms with that.